pull out your highlighter. And we're going to say, now we know how to graph the square root of x. And we know how to do transformations with the square root of x. But what we're going to add today is we're going to say, if you can graph the inside, you will now be able to graph the square root of that. So what does the square root of log of x look like? What does that graph look like? What does the square root of sine of 3x look like? What does the square root of x plus 3 cubed minus 5 look like? And we'll be able to do the square root of any graph. If we can graph the inside, we'll be able to graph the square root. So up till now, we've just had the square root graph. It's been pretty straightforward. What we're going to look at is a new technique. So we're going to talk about our old technique of graphing the square root of x plus 4. You would take your square root graph and you'd use transformations and move it 4 to the left. Can you see that that blue graph is just the square root graph moved 4 to the left? But now we're going to say, how could I use the graph of my inside function? How could I use the graph of x plus 4 to help me graph the square root of x plus 4? So the red graph is just the inside x plus 4. Now some of the things we're going to notice about the red graph and the blue graph is there are 2 points that are the same. -3, 1 and 4, 0. So the first question we have is, why do those points stay the same? Why are those the only points that are the same? And what do they have in common? Well, what happens when we plug in x equals -3? -3 plus 1 is, I'm sorry, -3 plus 4 is 1. So on my red graph, and this is my red graph right here, on that graph, can you see that if you plug in -3, you get 1? So it makes sense that we have the point -3, 1. On the blue graph, which all that we're doing is taking the square root of the other graph, why do we also get 1? Well, plug in -3. -3 plus 4 would be 1. What's the square root of 1? 1. So any time that your y value on your original graph is 1, if you're just square rooting it, the square root of 1 is going to stay the same. Can you see the same thing happens with 0? What's the square root of 0? Still 0. But if I take another point on my original red graph, like this point 0, 4, if my y value was 4 on the original graph, does it make sense that plugging in 0 into my blue graph, I'm going to get 2? Because what's the square root of 4? It's 2. So all we're doing is we're square rooting our y values. And some of our y values are going to stay the same. If the y value is 0 or the y value is 1, it's going to stay the same. So one of the first things that we're going to do with this new graphing technique is we're going to graph the original function, and we're going to find these points 0 and 1, which stay the same on both graphs. Then we're going to find any other nice points that we can, like the square root of 4 is 2, so I can plug in 0, 2. The next thing that we're going to talk about when graphing is when considering the y values, whether our new graph is going to be above our old graph or below our old graph. So when I'm talking about the old graph, I'm talking about the red one, or the inside graph. Can you see in this section right here that the y values of my blue graph are less than the y values of my red graph? And when I'm talking about y values and comparing them, when I'm comparing y values, the x value isn't changing. So I can compare the point 0.04 and 0.2. I can compare the point 2,6, and on this graph, I guess I would have 2, square root of 6. And my blue graph is below my red graph. So when I'm talking about the blue graph being below the red graph, it's because when you compare y values, the blue's y values are lower than the red's y values. And that's because what happens when you take a square root of 4? You get 2. You get something less. What happens when you take the square root of 9? You get 3. You get something less. And most people, because you mainly deal with whole numbers, get this idea that square rooting always makes a number smaller. But that's not always the case. Mental math. What's the square root of 1/4? Right? We can square root the top, get 1, square root the bottom, get 2. Which is bigger, 1/4 or 1/2? 1/2 is bigger. This is an example of square rooting something and getting a bigger value than you started. And so whenever our y values are between 0 and 1, the blue graph here is going to be slightly above the red graph. Let's look at one more example. Then we'll summarize these. Then we'll do some actual examples and write out the steps and stuff like that. Here we've got another graph. If you were having to graph this one with transformations, you see you have a horizontal reflection and a horizontal translation. What do we have to remember when we have both of those? We have to remember to factor first. So if you were doing transformations, that plus 2 is going to move it not 2 to the left, because you'd have to factor first. And now, can you see with the blue graph that you've had a reflection over the y-axis and moved 2 to the right? Does that match up? Okay. Can you see yourself forgetting to factor out the negative and accidentally going 2 to the left? Yes. So this would be a tricky one to graph because of that factoring note, and you might make mistakes. So in this case, you might actually like this new technique better. The new technique says, graph the inside first, negative x plus 2. Well, that would have a y-intercept of 2, a slope of negative 1. That's this straight line. Are there any places where it's equal to 0? Any places where it's equal to 1? Well, what's our x-intercept? That's at 2, 0. If I plug in 1, negative 1 plus 2 is 1. I have 2 points that aren't going to change. Because what's the square root of 0? It's 0. What's the square root of 1? It's 1. Are there any other nice points on here? Well, look. Right here, it looks like I have the point negative 2, 4. So on my blue graph, I'm going to have the point negative 2, 2. Everywhere where the y values are bigger than 1 on the red graph, the blue graph will be below. Any places where the y values on the red graph are between 0 and 1, the blue graph is slightly above. Whew, you can barely tell that that's slightly above. Okay? But you need to show, sometimes you can just barely do it, but you need to show that it is slightly above. Why in both of these graphs does my blue graph stop here? Why doesn't it continue? Again, if we think about the y values of our red graph, what do we notice about our y values of our red graph here or here? They're all negative. And so if they're all negative, can you take the square root of a negative? No. So our blue graph does not exist where our red graph is negative. So all of these are summarized on your next page. So if you want to take out your highlighter again, we can highlight these important ideas. 0 and 1. Those points are going to be on both graphs. They have a special name. They're called invariant points. So the first thing we're always going to do is see if we have any points that are, y values are 0 and 1, and those points are going to stay the same. If your graph lies between y equals 1 and the x-axis, in other words, when y is between 0 and 1, the square root graph will be above the original graph. And anytime your y values on your original graph are above y equals 1, your square root graph will be below. And finally, wherever your original graph, the y values are negative, your square root graph will not exist because you can't take the square root of a negative number. So let's look at example 1. Example 1, the graphs are given to us. So if we want to write out our steps off to the side here, we're going to plot the points where y is equal to 0 and y is equal to 1 on the original graph, if they exist. Sometimes you won't have those points. So in A, do we have any x-intercepts where the y value is 0? Yes. We have one right here at -2, 0. The y-coordinate would be 0. I labeled that point because I could, because it was nice. Sometimes you're going to get x-intercepts or values where y is 0 or y is 1 that aren't that nice. For example, on this one, can you see that y is equal to 1 right there? It's not perfect on my grid. I might estimate, it looks like it's at -1.5, 1. That's probably a pretty accurate estimate. But it's not right on a grid point, and that can happen sometimes. So step 1, we're going to plot the points where y is equal to 0 and y equals 1 on the original points. Plot any other nice points, if possible. Zero and 1 are nice points because you can take the square root of 0, you can take the square root of 1. So what you're looking for in nice points, is there any other y-coordinates that you can square root easily? I can square root 4 easily. Do I have? Yes, right here. I have the point 0, 4 on my original graph. So if I square root 4, I'm going to get 0, 2. Do I have any other nice points? Well, it kind of looks like I have 2.5, 9. So if I square rooted that, I would have 2.5, 3 on my square root graph. Step 3, when the y values are between 0 and 1 on the original graph, which I'll write just as y equals f of x, then the graph of your square root function is above. And whenever your y values are above y equals 1, your square root graph is going to be below. Now, particularly the second part is going to be obvious, especially if you've done some extra nice points. Because basically right now what we're going to do is we're going to play a little bit of connect the dots. And in this section for connecting the dots, that seems pretty obvious. Can you see that in that section the blue graph is below the red graph? Especially when I consider specific points like 2.5, 9 and 2.5, 3. While 2.5, 3 is very obviously below 2.5, 9. And 0, 2 is below 0, 4. So when we're talking about graphs or the graph being above or below, what I'm looking at are the y coordinates for the same x coordinate. Like when the x coordinate is 0, my blue graph is below my red graph. And because we had some nice points and we just connect the dots, it naturally happened. Where step 3 is harder is the place where your original graph, the y values are between 0 and 1. That's in this section here. And in this section, you need to show your blue graph being slightly above. So you can see a little bit of the red graph underneath. That's fine. So I just need to show it slightly above. If you over-exaggerate how much above, like I have done here in the purple, this would lose a half a mark because we went back in time. Can you see that this doesn't even pass the vertical line test? It's no longer a function. So if you over-exaggerate going above, you can also lose a half a mark. So this part gets a little bit tricky. You need to show, take away that purple, you need to show that it's slightly above. Sometimes the best that you're going to do is have it like almost on top of the graph when you're drawing it. And you're going to see in our next example some ones where, wow, it's really hard to show that it's slightly above. So on the exam, if it's like right on the line and they can't tell if it's above or below, they'll give it to you saying, okay, it looks like they tried to make it above. State the domain and range. Domain for this one, x is bigger than or equal to -2. Our range for this one, y is bigger than or equal to 0. For the second one, go through those same steps. First of all, we're going to look, are there any places on that original graph where it's equal to 0 or 1? Yes, we have an x-intercept right there at 6, 0. We look on our y-axis where 1 is, and sure enough, we have the point 4, 1. Step 2, do we have any other nice points? Not really, because the next nice point would be the square root of 4. So we don't really have any nice points. Does anybody know what the square root of 3 is? square root of 3 is about 1.7. So you could add it on there if you wanted to. But if you don't know it, that's all you would have was those first 2 points. Then you really have to know step 3. Because step 3 says when the y values are bigger than 1 on our original graph, our blue graph will be below the red graph. And when our y values on our original red graph are between 0 and 1, and this one's easier to show it above, that section, our blue graph, will be above the red graph. In example A, I use set notation. In example B, I'll use interval notation, just to remind you of that. In interval notation, our domain would go from negative infinity to 6 and include 6, and our range, smallest value is 0 and goes to infinity. Questions for practice on this one are number 5.